getting a lot of excitement around prolific and this new direction. It feels good.
We can see how much the optogenetic cells are actually getting activated. We can see.
I feel like it's at the finish line, and this is really it. It's actually happening. I feel very, very proud of that.
This is real, and not real as a science experiment, but real as a technology that can change the world, that can change products in the way that we've been thinking about it.
We saw an opportunity to move faster if we explored our photomolecular biology approach with therapeutics, using the light in the bioreactors to get cells to make medicine that is better quality and costs less.
There are certain proteins that could be super useful for treating certain diseases, but they fail very early on in the screening, and so they're just discarded right from the beginning.
These types of biotherapeutics that classically using conventional biomanufacturing methods are really difficult to make. By leveraging our optogenetic technology and using our platform, we can make really directed modifications to the cells that are producing these drugs and use that to our advantage.
So far, we've controlled cells in small reactors. They're made out of glass, which you can shine light through relatively easily. And that works super well at small scale, but we're going to show that this works at 200 liters in a stainless steel reactor with no light coming in. That's super cool. That's a big milestone.
Cell culture always starts in the lab. It starts at a very small scale. We've gone from scales like this to much larger scales. In this case, the 200 liter. And using optogenetics to illuminate a bioreactor, we've gone to modules such as Steelix, which is our first at-scale illumination using optogenetics. These tubes illuminate and activate the cells so we can realize the promise of optogenetics in cell culture, which can revolutionize the way we grow cells, the way we have cells produce protein, and the way they metabolize nutrients themselves. This is kind of a less expensive way because we can simply illuminate the cells with light. The cells are engineered then to receive that light. They read it, they activate certain metabolic pathways that allows the running of a reactor like this to produce a therapeutic in a much more cost-effective fashion.
There are limited technologies that can really help fine-tuning the expression. With chemicals, you put them on the cell and then it's an on and off switch. You don't really get the fine-tuned control.
Even outside of nature, just in biomanufacturing today, the main levers that we have to pull to affect cellular pathways are using chemicals, temperature or pH. These cause effects on many different systems and pathways within the cell. What optogenetics unlocks is like a noiseless, precise control of the systems that we care about. By combining that with closed-loop control, we can monitor what we care about in real time and then just make precise effects on the pathways that we care about. So it's taking cues and adjusting the lights in real time, closing the loop between the machines and biology.
I think we've barely scratched the surface of what optogenetics can do.
I think it will allow us to open up new therapeutics that can't currently be produced.
I feel very, very proud of that. And very proud of the team for all that we've been able to do.
We learned so much more about optogenetics at scale and in suspension, work that's never been done before.
But there's so much more that we can do. It's frankly hard not to be excited.
There is so much that this technology could do.